Welcome to Mrs. Neller's notes for her pre-calculus class. These are the notes for section 7.5, day 2, entitled More Trigonometric Equations. And we have basically two more examples that we have to get through with other trigonometric function solving techniques. And what we need to do today is take a look at when we have multiples of angles or a fraction of an angle. Okay. So our first example here is example 5. And what we're going to do is we're going to solve for theta just like we've been doing. And then we'll take a look at specific solutions. Okay? So in part A, when we're finding our solution, let me go to the next slide here. Okay? We have our equation 2 sine of 3 theta minus 1 equals 0. So we're going to find all the solutions. And again, remember when it says find all, that means we want to do the plus 2k pi. So if I was going to solve this, even if that 3 wasn't there, this is the new part for today, is having that 3 in front of the theta. So even if that wasn't there, I would still add the 1 over and divide by 2 so I can get the sine of theta, or in this case, the sine of 3 theta, by itself. So that's what I'm going to do. So then if I add the 1 and divide by 2, I'll have the sine of 3 theta equals 1/2. Now, I'm just going to think of this theta or this 3 theta, just like a theta for a moment. Okay, and I'm just going to think, okay, where is theta equal to 1/2 on my unit circle? And it's sine, so I need all students not taking calculus. I need the first and the second quadrants so that my sine value can be positive. And I have to think, okay, where is sine equal to 1/2? Well, if this was just regular old theta, I would say it's going to be pi over 6 and 5 pi over 6 in the second quadrant. Those are the radian values that have a terminal point that have a sine of 1/2. Okay? So now the only difference is I'm going to put a 3 in front of that theta because I had a 3 theta in my problem. Okay? So I leave the 3 there, but I still think of it like we have been as far as finding the radian. Okay? But now I'm not really solving for 3 theta. I still need to solve for theta. So I'm still going to divide by 3. Okay? So theta now will equal pi over 18. Or theta will equal 5 pi over 18. Okay, so these are going to be my principal solutions. And now if it was a normal general solution, I would add the 2k pi. Let me switch colors for just a moment. Okay, so I would add a 2k pi because it's sine. Okay, but remember I'm dividing by 3. So I'm going to add 2k pi divided by 3. So now I have all of my general solutions. I have all of the solutions. So if you have a multiple of an angle, you basically treat it the way we've been solving our trig equations, and then you just divide by whatever that multiple is. You divide your radian answer by that, and you divide the 2k pi or the k pi by that as well. Now, we had a part B that said find the solutions on the interval 0 to 2 pi. Okay, so if I have, let me write my solutions from part A again. I have pi over 18 plus 2k pi over 3. And then I also had 5 pi over 18 and 2k pi over 3. Okay, those are my two solutions that I got. But now they want me to find the solutions just from 0 to 2 pi, so one trip around the unit circle. So this is where we need to think of the values for k. Now, if my k value was equal to 0, I would get my my principal solutions, just 18 pi, pi over 18 and 5 pi over 18. So if I substitute in a 0 here, 0 times 2 times pi is 0 over 3 is still 0. Add that on and you get pi over 18. Or if I substitute in a 0 in here, 0 times 2 times pi is 0, divided by 3 is 0, plus 5 pi over 18 is 5 pi over 18. Okay? So I start with my principal solutions, and then I have to think, okay, my answers are going to be over 18. It's always going to be something over 18, something pi over 18. So that means that if I go to pi, that would be like 18 over 18. And if I go around to 2 pi, that would be 36 over 18. So I need to keep going around and adding the 2k pi over 3 until I get close to, but not over, the 36 pi over 18. Okay, so let's try a k value of 1 and see what that gets me. So if I substitute in a 1 here, I'll have 2 pi over 3. So if you do 1/18 plus 2/3, you'll get 13 over 18, or 13 pi over 18. And then substitute 1 into the other answer as well. So again, I have 2 pi over 3 that I'm going to add to 5 pi over 18. So add those fractions together and you'll get 17 pi over 18. So I still haven't gone past my 36 pi. At 17 pi over 18, I'm very close to pi. So I've got some more k values that I can use. So let's try 2. Okay, so now 2 times 2 will be 4. So this is 4 pi over 3 that I have to add to pi over 18. That gets you 25 pi over 18 when you add those fractions together. And then if I substitute in a 2 here, again, this gets me 4 pi over 3 plus 5 pi over 18. That gets me 29 pi over 18. So that's very close to my 36. And if I went further, if I tried to do a k value of 3 and substitute it in there, I'll get 2 pi because I'd have 6 over 3, which is 2 pi. So if I add 2 pi to the 1 over 18, then I've gone past my 2 pi limit anyway. Okay, so these are the k values that I needed to get all of these actual values to go from the interval 0 to 2 pi. Okay, so we're going to try that again in this example. We're just going to be working with tangents now instead of the sines. And we're still going to find all the solutions to the equation, and then we'll find them on the interval 0 to 4 pi this time. Okay. Now if I look closer at my equation, I notice that I have theta over 2. So instead of having a multiple of an angle, I have a fraction of an angle. But again, we're going to start off this problem just pretending that it was just tangent of theta. Okay? So if this dividing by 2 wasn't there with the theta, if it was just square root 3 tangent theta minus 1, I'd have to start by solving for tangent theta. So I would add the 1 over and divide by the square root of 3. So that's what I'm going to do. I'll have the tangent of theta over 2 equals 1 over the square root of 3. Now you could rationalize that if you wanted to. If you multiply by the square root of 3 on the top and bottom, you'll get square root 3 over 3. Okay? But remember, tangent is sine over cosine. So I have to think on my unit circle. Okay, I want the first quadrant. In that first quadrant, what sine value and what cosine value, if I put them in a fraction, would reduce to 1 over the square root of 3, or square root 3 over 3. And if I had a sine value of a half and a cosine value of square root 3 over 2, when I simplify that, I'll multiply by 2 over square root 3. So then that will get me the 1 over the square root of 3. Okay? And then if I rationalize that, then I would get the square root 3 over 3. Okay? So I need the sine value to be 1/2 and the cosine value to be square root 3 over 2. So that's going to get me a value of pi over 6. And in the third quadrant, that would be 7 pi over 6. Now again, remember, we're thinking of it in terms of theta, but then I'm going to put in that dividing by 2 as well. Okay? Now, before I go any further, we have to remember that tangent has a restriction on it. Okay? We only need our solutions to go from 0 to pi for tangent. So I actually don't need this value here. I just want to stay in this first quadrant, because if I go into the third, I'm going to go past 0 to pi. Really, tangent, remember, is restricted to the first and the fourth quadrants for our values that we've talked about in the past. So that 7 pi over 6, I don't need it for this problem. Okay? So to finish solving now, I have to get rid of this dividing by 2 that's going on with the theta. So I'm going to multiply both sides by 2. Okay, so times by 2, times by 2. And now I'll have 2 pi over 6, which is pi over 3. Now, normally for tangent, we add on an extra k pi. But again, I'm multiplying by 2. So I'm going to add on a 2k pi. Now I'm not doing that because I'm forgetting that the 2k pi really goes with the sine and the cosine functions. This 2 is coming from this 2 that I had to multiply by to get rid of the dividing the theta by 2. So if I had been dividing by 3, then I would have had 3k pi. If I was dividing by 4, I would have had 4k pi. So it's just coincidence that it's a 2k pi here. Okay, so that's my only solution for this equation. And now for part B, I'm going to find the solutions on this given interval. So again, let me write down the answer from the previous slide. We had pi over 3 and then 2k pi. Okay, and I want to go from 0 to 4 pi. So really, that means I'm going to go around my unit circle twice. So again, I have to think of the k values that I could substitute in that would keep me from going over that 4 pi limit. Okay. So I always start with k equaling 0. And basically, when I substitute that in, I just get the pi over 3. I get the principal solution that I started with. Okay. And if I tried k as 1, if I put a 1 in here, then I would have 2 pi. And 2 pi plus pi over 3 would be 7 pi over 3. And if I made a k value of 2, 2 times 2 would be 4 pi, plus a third would go past this 4 pi limit that I would have. Okay, so these are my only two answers for k values of 0 and 1. So this concept of the k value, we've kind of talked about it before in the last section and in section 7.4. And haven't really dealt with it specifically, so that's something new that's in this section. And then remember that if you have a multiple of the theta, or if you have a fraction of the theta, just set up the solution like it's a regular theta value, and then either divide or multiply by that number that's being multiplied or divided by theta, so that way you can adjust your answer. And you have to adjust your radian measure and your 2k pi or your k pi values as well. So there's a lot of little details, but again, it's all based on algebra. So work through these problems, show your work, show those algebraic steps that you're doing. Um, have your calculators ready if you need help with those fractions when you're adding the fractions and substituting in the values for k. Remember, the solutions are all worked out in the binder in the classroom. And if you have any questions, come see me before school.